Hi, in this video we are going to talk about the implementation of the topological ordering shortest path algorithm. So if you may recall that, for example, the Bellman-Ford algorithm has the running time ordo V times E, where the V denotes the number of vertices and the E denotes the number of edges in our graph. And this complexity can be reduced to ordo V plus E if the graph has no cycles, so it is a directed acyclic graph with the half of topological ordering. So we have the vertex class, we have the string name, we associate a name to every vertex, we have a reference to a predecessor or the previous vertex, we have to store whether it has been visited or not, we store a list of edges to store the adjacencies list, so to store the neighbors of this vertex, and of course the minimum distance we have to store, we initialize it to be a maximum value. And these are just the getters and the setters, and of course I have to override the toString method to get the name of the vertex. So that's all about the vertex class. Then I have the edge, as we have discussed in the DAG algorithm, for example, or the Bellman-Ford, that I have a weight associated to each edge, and I store a reference to a start vertex and to a target vertex. And I set these properties in the constructor when we instantiate this given edge class. And of course I have the getters and the setters for these properties. So this is the edge. Then I have to make a topological sort or a topological ordering, and I use a stack as a data structure. So to make a topological order, I will get a list of vertices, the vertex list, and I just do a simple depth first search. When we are discussing topological ordering or topological sort, we saw that a way of making topological ordering is depth first search. So we go through all of the vertices, and if they are not visited, we call the depth first search method recursively. And here I just have to get the adjacency list, so I visit each of the neighbors, set it to be visited, and just call it recursively on the adjacent vertices. And then at the end I push it to a stack. And when I get to topological order, I just reverse it. There's a method in the collections class called reverse, or it may be an interface, I'm not sure. We just have to reverse this stack data structure and going to return it. And whenever we want to use, this is the acyclic shortest path class, we get the vertex list storing all the vertices. We have the source vertex and the target vertex. And it's very similar to DAG and Bellman-Ford algorithm. We just set the minimum distance to the source vertex to be 0 because that's where we are standing. We instantiate the topological sort class. We make the topological order first on the vertex list. Then we get the topological order. It's going to return a stack, as we have discussed. And we keep iterating through this stack as a vertex, just print it out, and we visit all of the edges of this actual vertex. We get the adjacency list, and basically it is the same as we have discussed. So this is the topological ordering, and of course I use it that whether the min distance is equals to max value, then no shortest path exists, and as there's a shortest path to the given target vertex we have specified here. So here when I run it, yeah, it's in Hungarian. I write here, just remind me that whenever we use the knapsack problem, we can construct a tree-like structure, and it is always directed acyclic graph. So we can reduce the knapsack problem, which can be solved with dynamic programming. We can solve this problem with the help of directed graphs, and we just have to use the shortest path algorithm. And because it's a DAG, we can use the topological ordering shortest path, which is very fast, because that's the Dijkstra's algorithm time complexity, E plus V times log V. The time complexity for Bellman-Ford is E times V. It's much slower, and E plus V for this topological ordering shortest path. So it's very, very fast, linear time complexity. So for example, we have this A, B, C, D. We have the edge weights accordingly, and if I run it, it is going to yield no shortest path there. We have to specify, for example, from A, B, there's a vertex list add. Okay, there's a edge 3 from 0 to 1, then 1 to 2, then 2 to 3, and 0 to 3. So whenever we want to go from 0, vertex 0 to vertex 3, vertex 0 to vertex 3, it is going to yield 9, because the shortest path is to go from A to B, B to C, and C to D. Because to directly go from A to D, it would give us 50 cost, and 3 plus 3 plus 3 is just 9. If I set it to 1, then the shortest path will be directly from A to D. And it is A. It is going to, something's not good with the, because the cost is good, it's going to take 1, but maybe I forget to set the target shortest path. Yeah, because I iterate through in the topological ordering, I guess. Or where is this A, B, C, D come from? A, B, C, D. I'm not sure that. I found it that it comes from here. That we print out the actual vertex, and that's why we print out all of them, because we go from A to B, C, D, we iterate through all of the vertices. So it's just going to show us the sequence in which we have to go. It is just, I'm going to get rid of this because it's misleading. The shortest path here is 1. Whenever we set the direct solution from A to D to a very, very minimum cost. But whenever it's very, very expensive to go directly from A to D, it is going to yield us the good solution, A to B, B to C, C to D, and that's going to cost 9. So our DAG topological ordering shortest path algorithm works fine, and this is how to solve this shortest path problem when we have directly the cyclic graph. Thanks for watching.